quantum mechanical explanation of normal Zeeman effect. As we know, the normal Zeeman effect is produced whenever a spectral line is placed in a comparatively strong magnetic field. So, in presence of the strong magnetic field, a single spectral line is found to be split up into two or three components depends upon the direction of observation, and the lines got split up, or the splitting of the lines or the spacing between the outer components from the inner components can be varied by varying the external magnetic field, strength of the external magnetic field, and so on. Okay, now as we know, the normal Zeeman effect is a splitting of the spectral lines into two or three components when placed in strong magnetic field is called normal Zeeman effect. The components are symmetrically distributed about the original line. The upper component has higher frequency than that of the original line, and the inner component has less frequency than that of original line. These are the observations which are obtained for the normal Zeeman effect, and today, using the quantum mechanical theory, we have to prove these assumptions or these observations theoretically. Okay, so for that, for the quantum mechanical explanation of normal Zeeman effect, or to explain the normal Zeeman effect using quantum mechanical theory, we have to consider only the angular motion of an electron, and we have to leave its spin. As we know, the electrons have angular or orbital as well as spin motions, but as far as the normal Zeeman effect is concerned, we need to consider only the angular motion, and hence now the electron has orbital angular momentum given by L equals to capital L equals to under root of small l, L plus 1 into h cross. It is the orbital angular momentum possessed by electron, where small l is the orbital quantum number. Okay, and from the orbital angular momentum we can find out the value of magnetic moment possessed by an electron. So the magnetic moment will be E upon twice m, that is called gyromagnetic ratio. It is a electromechanical ratio for an electron into the orbital angular momentum. The magnetic moment of an electron is always equals to a gyromagnetic ratio and the orbital angular momentum. Okay, so put the value of capital L from equation number 1. Hence we can write here as a value of small l equals to L into L plus 1 h cross. So here I E into h cross into under root of L into L plus 1. Okay, but the quantity E h cross upon twice m, that is called Bohr magneton. It is called the Bohr magneton, and it is the Bohr magneton is smallest unit for measurement of magnetic moment of an electron. Okay, the value of this Bohr magneton is a constant quantity because E is having the same value, h cross is constant, and mass of electron is also constant. Therefore the value of Bohr magneton is constant in this case. Hence the magnetic moment of an electron can be written as mu b into under root of L into L plus 1. Okay, under root of L into L plus 1. So now in this connection, up to the equation number 2, where we have find out the value of magnetic moment of an electron. It is obtained before the application of magnetic field. Means these are the values purchased by electrons before enters in a magnetic field, okay, or before the application of external magnetic field to the spectral lines. Then now what happens after the application of magnetic field? When an atom, actually for this case we can say that when a spectral line is placed in an external magnetic field, but the spectral lines are caused by the transition of electrons within various energy levels. Hence we have mentioned here that atom is placed in an external magnetic field having strength B, then the vector L, that is called the orbital angular momentum vector, precedes about the direction of field. Okay, the precessional motion, as I have told you in the last year, the precessional motion is the motion on the surface of cone or ice cream cone or any cone, the motion on the surface of cone, that is called the precessional motion. And the precession of electrons orbital momentum vector in presence of magnetic field, that is called a Larmor's precession. Okay, and due to the Larmor's precession, the angular velocity achieved by electron will be omega L equals to be upon twice m. It is having also a constant quantity for the same magnetic field. Okay, it is our equation number 3. So what happens due to the more angular velocity, due to the precession of L, that gives additional energy to the electron. Due to the precession, what happens, the electrons got additional energy, it got additional energy, and the interaction energy of an atom will be delta E equal to mu L into capital B bar, vector product, scalar product of the mu L bar into B bar. Okay, as we know, A bar dot B bar equals to AB cos theta, where theta is the angle between these two vectors. So for this equation, we can simplify to mu L in mu L B cos theta, where theta is the angle between L and B. Okay, so it is our equation number 4, and equation 4 gives you the value of additional energy achieved by electron due to the precessional motion of orbital angular momentum vector. Okay, so this precessional motion is shown in the figure. So this motion on the surface of cone, here vector L rotates or moves on the surface of cone. Okay, with an angle of theta. Here theta is the angle made by this vector L with the direction of external magnetic field. Okay, now here the value of OP, here there is a point O, the value of OP will be ml into h cross. Again the right triangle is produced here. This right triangle is having hypotenuse of capital L, angle is theta, and adjacent side is ml into h cross. So for this figure, we can find out the value of cos theta. So cos theta will be equals to adjacent side upon hypotenuse, that is ml into h cross divided by capital L. Okay. Now put the value of capital L from equation number 1, which is under root of small l, l plus 1 into h cross. Okay, so h cross on numerator and denominator got cancelled. Hence the value of cos theta will be ml upon under root of l, l plus 1. So now put this value of cos theta in the equation number 4, which is the interaction energy of an electron or the additional energy achieved by electron. So put here cos theta. Therefore, the equation for delta E will be delta E equals to mu L into B, mu L into B into the value of cos theta, that is ml upon under root of small l, l plus 1. Now put the value of this ml, value of ml will be or mu L will be mu B into under root of small l L plus 1, where mu B is the Bohr magneton. We have put these values from equation number 2. Let us see the equation 2. Equation 2 will be mu L equals to mu B into under root of L L plus 1. Okay. So put this value in equation number, this equation of interaction energy. The equation will be mu B into under root of L plus 1 into B as it is into ml as it is upon under root of L plus 1. So this under root of L into L plus 1 on numerator and denominator got cancelled. So the equation becomes mu B into mu B into capital B into ml, mu B into capital B into ml. So the value of this mu B is E h cross upon twice m, okay, into B into under root of LL plus 1 into ML upon under root of LL plus 1. Okay, so these two square roots got cancelled. So the equation simplifies to the form E into B. Here H cross I have written on near to the ML here. Okay, H cross goes here. Therefore the equation simplifies to the form delta E equals to EB. Here E as it is upon 2m is also same. Here multiply E by capital B. Therefore the equation becomes EB upon twice m into H cross into ml, because the square root on both the sides got cancel here. But we know EB upon twice m, that is called omega L, from equation number 3. Let us see the equation 3. Equation 3 is omega L, that is the additional velocity possessed by electron, or the velocity of precession of an vector L. Omega L equals to BE upon twice m. So in place of the BE upon twice m, we can put omega L. Therefore the equation for interaction energy simplifies to the form omega L into H cross into ml. That is our equation number 5. We have put the value of omega L from equation number 3. Okay. Now it is the amount of interaction energy possessed by electrons. Now we can simplify this equation. I have written the equation as it is, omega L into H cross into ml, but we know omega equals to twice pi by t. That is our basic equation for the angular or the circular motion or the periodic motion. In place of 1 by t, we can write the frequency, that is nu. So in place of omega L, we can put here twice pi nu L, twice pi nu L. In place of the omega L, we have written here twice pi nu L, because we know omega equals to twice pi by t. Okay, it is our basic equation in the field of circular motion, orbital motion, or the periodic motion. 1 by t is frequency, that is nu. So we can write in place of the omega L as a twice pi into nu L, H cross as it is, ml also as it is, from equation number 5. Okay, now we know H cross equals to H upon twice pi. So this twice pi from numerator and denominator got cancelled, and hence the equation simplifies to the form delta E equals to nu L into H into ml. Okay, let's remember here, delta E equals to nu L into H into ml, because twice pi on numerator and denominator got cancelled. It is our equation number 6. Okay, now we know the ml has total number of twice L plus 1 values. Okay, its values always ranging from minus L to plus L, or plus L to minus L, including 0. Means for a particular electron, if the value of L is 1, then its values of ml will be plus 1, 0 and minus 1. Okay, and so on. If it has value of plus 2 or 2, then the values of ml will be 2 into 2 plus 1, that is 5 values ranging from minus 2, minus 1, 0, plus 1 and plus 2, and so on. Okay, so under the action of magnetic field, we can say that a single energy level is split up into twice L plus 1 components, twice L plus 1 total components, and its number of components which are splitted depends upon the values of L, that is depends upon the position of electron in a particular orbital, because the values of L denotes the number of orbitals, that is s orbital, p orbital, d orbital, f orbital, and so on. Okay, now for this present case, for the explanation of normal Zeeman effect, let us consider the transition between energy levels, that is energy level having L equals to 2 to L equals to 1. Means we have to see the transition from D state to the P state. Electron in a D state to the electron in a P state. During this transition, what happens? Or how the spectral lines got split up into several components. Okay, you can take the transition between L equals to 1 to L equals to 0. Okay, in that case the splitting will be less in number. Now for the present case, we can imagine here E1 as a energy of energy level L equals to 1 in the absence of magnetic field, and after the application of magnetic field, as we know, the electron's angular velocity increases, it got the some interaction energy, and therefore the energy of energy level in presence of magnetic field will be EB1. Here see the name as a EB1. E1 is the energy of first level, and B depends upon, or B refers the energy in presence of magnetic field. Okay, so up to equation 6 we have calculated the interaction energy of energy levels achieved by energy levels in presence of the magnetic field. Now we will see, or we can find out the splitting of spectral lines by considering the transition between particular two energy levels. Okay, now the present case, for the present case we have considered, we have chosen the two levels having L equals to 2 and L equals to 1, that are the D state and P state energy levels. Okay, now for the P state energy level, its energy before magnetic field will be E1, energy after the magnetic field will be EB1. Obviously we can write EB1, that is energy in presence of magnetic field, equals to energy in absence of magnetic field plus increase in the energy in presence of magnetic field, or increase in energy due to the application of magnetic field, or plus interaction energy. Okay, because the increase in energy is equal to interaction energy, means we can simplify the equation as EB1 equals to E1 plus nu L H ml1. Okay, I have substituted this value of delta E from equation number 6. Okay, here equation 6 is the nu L, actually here nu L is there into H into ml, into ml. Okay, so it is our equation number 6. Here for the first level, to separate the ml for both the levels, I have substituted, or I have put one substitute, one suffix as a 1. Okay, so the energy of D state, sorry, P state in presence of magnetic field equals to energy in absence of magnetic field plus nu L H ml1. That is our equation number 7. Similarly, we can find out the energy for the second energy level, that is energy for the D level. So for that, let E2 will be energy of L equal to 2 level in absence of magnetic field, and EB2 will be the energy of energy level L equals to 2 in presence of magnetic field. Similarly, we can write here EB2 equal to E2 plus delta E. Here EB2 equal to E2 plus nu L H ml2. In the previous equation, we have written here as a ml1. Okay, we have written here ml1. Now for this case, just separate the two state. We will put here 1 and 2 as a suffix. Okay, so equations 7 and 8 are nearly same. Both these equations will give you the value of energy possessed by both levels after placing in a magnetic field. Okay, now whenever we want to study the splitting of spectral lines, we must have to show the spectral line or energy of the spectral lines. So the quantum of energy radiated in presence of magnetic field will be, now we have two energy levels here. E2 is there, sorry, EB2. Here we have EB2. Okay, and now we have another level EB1. Here we have a level EB1. Okay, and whenever the electron makes transition from EB2 to the EB1, the quantum of energy, that is h nu, is emitted. Okay, h nu is emitted in this case, and this emitted energy is the energy of spectral line. Okay, so now calculate the quantum of that energy radiated when electron makes transition between EB2 and EB1 in presence of the magnetic fields. So it is obviously equals to energy of upper level minus energy of lower level, that is EB2 minus EB1. I have put there EB2 minus EB1. Now put the value of EB2 from equation number 8 as a E2 plus nu L H Ml2 minus value of EB1 from equation number 7. Just see here equation number 7 as E1 plus nu L into H Ml1. Okay. Therefore, our equation will be E1 plus nu L H Ml1. Now from both the terms E2 and E1 take in one bracket as a E2 minus E1 plus nu L into H. In both the brackets are common, nu L into H are common terms. Here in bracket Ml2 minus Ml1. So Ml2 minus Ml1 is the change in value of magnetic orbital quantum number during transition. So in place of the ml2 minus ml1, we can write here change in ml, that is delta ml. Change in ml as a delta ml. So the equation simplifies to the form energy radiated during the transition. As I have told here, as h nu. So h nu equals to E2 minus E1 is the energy change between two levels before the magnetic field. So it can be written as h nu 0 as the energy of original line plus h nu l h nu l into delta ml. Okay, so h on both these three, all the three terms got cancelled, so we can write the equation as a nu equals to nu 0 plus nu l into delta ml. Okay, so it is the frequency, because the above equation, it is the h nu means it is the energy radiated during the transition in presence of magnetic field. But now we have calculated the frequency of a spectral line in presence of magnetic field during the transition. Okay, so up till we have calculated most of the equation. Now move towards the next few equations. Here we can see that nu is the frequency of spectral line in presence of magnetic field, nu 0 is the frequency of spectral line in absence of magnetic field. Okay, I have told you this statement already, that for the D state it has how many? 2 L plus 1, that is 2 into, for the D state value of L is 2, so 2 into 2 plus 1, that is 5 sub levels. Also the P state has a value of L equals to, 1, so it has 2L plus 1, that is 2 into 1 plus 1, that is 3 sub levels. I have shown these sub levels for D state and P state on the next slide. Okay, simply see the remember here the number of sub levels possessed by D state electron and P state electrons. Okay, now applying the selection rules, because we know for any transition or for any spectral lines there is a particular selection rule, and whenever a particular transition obeys that selection rule, then those spectral lines are visible, all the other transitions and all the other spectral lines are forbidden. Okay, now the selection rule for this present case is delta ml equal to 0 or plus minus 1. Means in equation number 9, whenever the value of delta ml changes by 0 or increases by 0 or increases by 1 or decreases by 1, only these transitions are allowed transitions, or these are the spectroscopically allowed transitions. Okay, all the other transitions having delta ml more than or less than or different than 0 or plus minus 1 are forbidden transitions. Okay, means during a transition if the value of ml changes by 2 or minus 2 plus 3 minus 3 and all other values, these transitions are forbidden transitions for this case. Okay, so now by applying the selection rule, suppose if delta ml equal to plus 1, what happens from the equation 9? In equation 9 put delta ml equal to plus 1, so equation will be nu equals to nu 0 as it is, plus nu l in place of the delta ml put here plus 1, so the equation will be nu equals to nu 0 plus nu l. So it is one of the kind of spectral line that is shown by nu 1. Okay, when the selection rule is delta ml equals to minus 1, obviously the frequency of second spectral line, second kind of spectral line will be nu 2 equals to nu 0, in place of the plus we will write here minus nu l. Okay, and if delta ml equals to 0, the from equation 9 we can see that delta ml 0 means second term vanishes, and the equation becomes nu equals to nu 0, or we can mention here that nu 3 equals to nu 0 as a frequency of third spectral line. But as its frequency is similar to the original line, because we know here nu 0 is the frequency of original line, frequency of the spectral line in absence of magnetic field, that is the frequency of the original line. Okay, so we can say that in presence of the magnetic field three kinds of spectral lines are obtained, whereas in absence of magnetic field a single line having frequency nu 0 is obtained. Means here the frequency of one spectral line is more than, that is nu 0 plus nu l, means its frequency of the original line is more than nu l. Again, for the second case, the nu 2 equals to nu 0 minus nu l, so the frequency is less than that of the original line, and third kind of spectral lines having frequency equals to that of original line are obtained. Okay, where nu equals to omega l upon twice pi, that is b upon 4 pi m. Okay, now in the figure I have shown all these transitions, and the frequencies of spectral lines are shown in the here table as. Okay, see here in the absence of magnetic field, what happens in the absence of magnetic field, there is a single spectral line, okay, having energy E2, and energy of the lower energy level is E1, and electron makes transition from E2 to E1 having energy equal to or frequency equals to nu 0. Okay, means in a spectrum we have only a single spectral line as shown by here black color. It is a single line is obtained without magnetic field. See here, without magnetic field. In magnetic field or in presence of the magnetic field, we know a single spectral line in a D state, it got split up into 5 components having ml values plus 2, plus 1, 0, minus 1 and minus 2. Again, the P state is divided into or split up into 3 components having ml values plus 1, 0 and minus 1. So there are 3 kinds of transition. these are the transitions, these three are the transitions obtained when we use selection rule as a delta ml equals to minus 1, means a transition from ml equals to 0 to ml equals to 1. So 0 minus minus 1, that is minus 1. Okay, here for the second line, see here transition from minus 1 to 0, so minus 1 minus 0, that is minus 1. Third line is obtained from minus 2 to minus 1, so minus 2 minus minus 1, that is minus minus plus 1, so minus 2 plus 1, that is minus 1. So all these three lines are obtained when we use the selection rule delta ml equals to minus 1. Central lines are obtained when you use the selection rule as a delta ml equals to 0, means transition from plus 1 to plus 1, 0 to 0, minus 1 to minus 1. So that gives the central spectral line. And previous transition gives a frequency, a spectral line having frequency less than that of original line. And these are the transitions which are obtained by using selection rule as a delta ml equals to plus 1. So transition from plus 2 to plus 1, plus 1 to 0, and 0 to minus 1. Okay, so in this way, in presence of the magnetic field, we got three spectral lines. Means we can say that in presence of a magnetic field, a single line is split up into three different components. So that proves the results or observations of the normal Zeeman effect. In this way, we have proved the quantum mechanically the normal Zeeman effect. Okay, so it is about the explanation of normal Zeeman effect. Now, thank you.